Hey, North, Mr. Yergler here. This video is going to get into what's called salt hydrolysis. This is where things start to get a little complex and we start talking about conjugate acids and conjugate bases a lot. So kind of hang on and let's get started. Let's do a little thought experiment. What do you think would happen if we had just chloride ions in water? Or what if we just had fluoride ions in water? Do you think the chlorine would be able to form HCl and leave OH minus by pulling an H off of the chlorine? Or would fluorine be more likely to pull an H off of the water and form HF, leaving behind an OH minus? Which one is more likely? This is actually what we call hydrolysis. Because the chloride ion is not going to pull this off because HCl is a strong acid, so it dissociates completely, this reaction isn't really going to happen, but this one actually would a little bit, and that is going to affect the pH of a salt solution containing that fluoride ion. Now, in normal neutralization reactions, we've said that we start with an acid and we add a base to it, and that produces a salt and water. And I'm writing water as HOH because it kind of sometimes helps to do that, to see that water is essentially a proton with a hydroxide ion. Now, when we do a neutralization reaction like this, these result in salts, which is true, and we've always said that acids and bases produce salts and water. And in this particular case, it would produce a salt that is neutral, meaning it wouldn't affect the pH. KCl doesn't affect the pH of the solution that it's in, and that's because it comes from a strong acid and a strong base. But now that we've talked about weak acids and weak bases, it gets a little more complex. If you have an anion from a weak acid, like fluorine, because HF is a weak acid, it will actually grab one of the protons off of water in order to form its equilibrium with its HF molecule. That then leaves behind OH minus, which then leaves the solution slightly basic. You could say the same thing of the cation of a weak base, except that it would pull off the OH from the water, leaving behind an H+, and therefore an acidic solution. We'll go through a few examples. There's a couple different combinations. So we could have strong acids with strong bases. This is what you normally think of as a neutralization reaction, where you completely neutralize the salt and you end up with a neutral salt. We could have a strong acid with a weak base. That's going to leave us with an acidic salt. A weak acid with a strong base is going to leave us with a basic salt. And if we had a weak acid and weak base, then it's going to depend on the Kb versus the Ka. If the base is a stronger base than the acid is an acid, then it will end up basic. If it's the other way around, then it will end up acidic. So in short, you can kind of just say that the stronger one wins. If you have a strong acid, then it's going to end up with an acidic salt. However, it's okay to kind of have that memorized, or just kind of remember that to quickly identify whether a salt is going to make a basic or acidic solution. But it's also important to kind of understand why and what's happening behind the scenes. As a quick refresher, let's take a look at our strong acids. There's 6 of them that you should know, and then their conjugate bases are going to be all of the same molecule with all the H's removed, essentially. Compare that to our strong bases, all the hydroxides of group 1 and group 2, and so their conjugate acids are going to be all the cations from all those hydroxides. Now, if we take any one of these anions and any one of these cations and make a salt, like sodium chloride or sodium iodide or potassium chloride, they're all going to make neutral salts because they're all from strong acids and bases. It's when we mix in a weak acid or a weak base where things get a little more tricky. Let's go through an example. So let's say we take nitric acid, HNO3, and we mix it with some ammonium hydroxide, which is a weak base. It helps if we visualize what's kind of floating around in the beaker. We don't really have ammonium nitrate. We have ammonium ions and we have nitrate ions, right? What's the ammonium ions going to do? They're going to pull an OH off of water because it's a weak base. Because ammonium hydroxide is a weak base, it's going to gravitate back towards its original molecule, undissociated molecule. And in order to do that, it's going to have to pull an OH off of the water molecule. That's going to leave behind an H+, which is going to make it a slightly acidic solution. Now, is NO3 going to do the same thing and cancel it out? Well, think what it would produce. If NO3 hydrolyzed, then it would have to pull a hydrogen off of water and make HNO3. But HNO3 is a strong acid, and so that's not going to happen. So we're going to end up with a slightly acidic solution because we have the hydrolysis of the ammonium ion. We could look at it another way. What if we have just a salt that's given to us, like ammonium bromide? Is that going to make an acidic solution or a basic solution? Again, think of the ions that are involved here. We have ammonium ions, which, as I kind of have right here, are going to end up producing H+ ions. And then we have bromide ions. The bromide ions could hydrolyze theoretically to produce HBr and OH-. But that's not really going to happen because HBr is a strong acid. It's going to be 100% on this side of the reaction, right? So we're not going to be producing any OH-, so we're going to end up with an acidic solution. Let's look at another example. So a weak acid with a strong base. If we have phosphoric acid with lithium hydroxide, then it's going to do the double replacement reaction, produce the salt of lithium, hydrogen phosphate, and water. We're just considering the first proton in this case. Could the dihydrogen phosphate molecule or ion interact with water to go back to the H3PO4 that it came from? Well, if H3PO4 is a weak acid, which it is, then that will happen. And because it's grabbing that H+, it's removing it from water, and so it's leaving us with an OH- in solution. Meanwhile, the lithium hydroxide could theoretically hydrolyze back into lithium hydroxide and H+, but because it's a strong base, that's not going to happen, right? So we're going to end up with a slightly basic solution here. Meaning even if you just dissolve lithium bihydrogen phosphate into water, you would end up with a basic solution because of the prevalence of this ion to grab H's off of water and leave us with OH-. So another example, potassium fluoride, would it be acidic or basic? You could go ahead and pause the video and try and figure this one out on your own. Always look at the ions that are produced. So we're going to have potassium ions. Those could theoretically hydrolyze, grabbing OH off of the water molecule. Or we could have fluoride ions hydrolyzing to grab an H off of the water molecule. Which one is more likely? Well, we know that potassium hydroxide is a strong base, so that's not going to work. It's going to be 100% on this side of the reaction. Meanwhile, the fluoride ion will grab some H's because HF is a weak acid, and so there's going to be an equilibrium there, leaving us with a slightly basic solution because we're going to have those OH's. All right, one more example where we calculate the pH of a salt solution. So if we have a 0.3 molar sodium fluoride solution, and we have a Ka for HF, let's first think about what ions are present. The sodium ions are present. They could theoretically form sodium hydroxide, leaving us with H+, but sodium hydroxide is a strong base, so that's not going to work. The fluoride ions, however, could theoretically go to HF, which is a weak acid. So we know that we're going to end up with a basic solution because we have these OH's. Now that we know that we're going to have a basic solution, we need to figure out the concentrations of our species in order to find our pH. We know that we're starting with a 0.3 molar fluoride ion. The sodium ion is going to be a spectator, and so it doesn't really matter what concentration it's going to be. But it would be 0.3 molar, but that's kind of irrelevant. I'm going to skip the initial and change lines on the ice table and just skip right to the equilibrium line. So our fluoride ion is going to be 0.3 minus X, and our HF would be X, and our OH would also be X. This is where it gets really tricky. You really have to pay attention to this. I would highlight this or put a big star next to this. This Ka that we're given is the Ka of HF, which would be the amount that HF dissociates into its ions, which is essentially the backwards reaction here, right? We actually don't need this Ka, but we do need the Kb for this reaction. How do we convert a Ka into a Kb? There's this awesome, handy-dandy, wonderful formula where the Kw, the autoionization constant for water, 1 times 10 to the negative 14th, is equal to the Ka of any weak acid times the Kb of its conjugate base. So we can actually solve for the Kb. So we actually need to convert this into a Kb. I'm going to go ahead and do that by dividing, and you end up with a Kb of 1.4 times 10 to the negative 11th. Now that we have the Kb, this is the amount of dissociation in this forward direction, the way I have it written here. So now we can use this to set up a equilibrium expression. X squared over our reactants. I'm going to neglect X because our Kb is so small. And so then we're left with X equals 2.05 times 10 to the negative 6th. Always pause and think about what X refers to. X is referring to the OH minus concentration. So it's really, if you take the negative log of that, you're really going to find the pOH. Subtract from 14 to find the pH. So our pH solution of the solution will be 8.31, which is consistent. Always check yourself. It is consistent with the fact that we predicted that we would have a basic solution. So that's a lot of information that we just went through. It gets confusing with the conjugate acids and conjugate bases. It might be helpful to go back over certain sections of this video and kind of track with it mentally. If you have questions on it, if any part's confusing, make sure you make a note of that and bring it up in class so we can go over it. All right, this is Mr. Yergler signing out.